morning, everyone. And sorry the wrong title was up there, but today we'll be talking about building distributed systems. So just a quick show of hands. How many of you have built a distributed system from the ground up before? Anyone? All right, good. So there's probably more of you that have than you might actually realize, but we're going to add some structure to that. And then for the rest of you, the goal for the next 25 minutes is for you to learn the basic concepts that you need in order to start building your own basic distributed systems. So the way we are going to approach that is we'll start by going over the basic building blocks, and then we'll put those together with some live code, and then we'll see it all in action with a live demo that all of you can participate in, at least if those demo ghosts don't get in the way. So cross your fingers for that. All right, so just real quick, again, my name is James, and I'm the founder of Goldfire Studios, which is a small indie game studio based out of Oklahoma City. And our focus is on building massively multiplayer online games using web technologies. So things like JavaScript, Node.js, WebGL, so on and so forth. I'm also pretty heavily involved with open source, so we've published a bunch of different libraries with Goldfire, and I'm also the author of Howler.js, the audio library. Okay, so the first question that usually comes up when talking about building distributed systems is actually why. So if you're working on something like a side project maybe, or something that you don't expect to need to scale, you might be wondering why you need to add in the complexity of a distributed system and worry about maybe the different moving parts and things of that nature. So before we get into the building blocks, I just wanted to go over a couple of reasons why this is something you should be thinking about no matter what scale that you're at. So the first reason has to do with the simple fact that things are pretty unpredictable, right? So hopefully you might actually outgrow your single server. You know, you may, let's say you're working on a side project. You may have some small virtual server, and at some point you'll have to grow that up to a larger virtual server, and then eventually you're going to hit a bottleneck, and you'll need multiple servers for that. So you're going to need to build a distributed system. And if you've been thinking about that from the beginning, instead of when it's already an issue, your life's going to be a whole lot easier. Second reason is, I think, a lot more important because it applies across the board. And that's the simple idea of minimizing downtime. So it doesn't matter if you've got 100 users a day or 1 million users a day. A distributed system is going to help you minimize downtime, and that's something that's going to be important to all of your 100 or million users. And this is probably something that a lot of you can relate to. At least in our experience, it always seems that servers, for whatever reason, tend to know when it's least convenient for them to go down for the developer. And so for us, our servers would always crash in the middle of the night. And so I would find myself getting those dreaded monitoring ping notifications on my phone, having to wake up and figure out what was going on and get it fixed. And this is what sort of led to this talk eventually. We got to a point where we were having 2 to 3 outages per week, and for all sorts of different issues, but they all were caused by issues with servers or processes on those servers. And once we had implemented a distributed system and eliminated those single points of failure, we went from 2 to 3 outages per week to maybe 2 to 3 outages total in the last 4 to 5 years. So it's going to make your life a whole lot easier, and it's going to make your users a lot happier as well. So hopefully you're a little more convinced that this is something important to be thinking about no matter what stage you're at. And if you look at this diagram here, this is your basic distributed system, right? So when you start thinking about it, you might think it's going to be very complicated. There's a lot of pieces involved. But when you really boil it down to the basics, it's really, really simple. There's just 3 basic layers to it. And let's go ahead and look at those real quick. So the first layer is your load balancer. And most of you are probably fairly familiar with load balancers. Oftentimes, they're used to route clients to servers that are performing different functions. In our case, they will be used specifically to route clients to servers that perform the exact same function in any number of those servers. The other important function of the load balancer is performing health checks. So the load balancer will be checking to see if a server is up or down, and then routing clients accordingly so that they aren't landing on a non-functioning server or application. So there's a number of different options available for load balancer. HA proxy is one pretty popular option. It's open source, really feature-rich. It's been around for a long time, very battle-tested. So that's what we're going to use in today's demo. But there are other options such as Nginx, more commonly used as a web server, but it does have a nice load balancer built in as well. And Envoy is sort of a newer entry that has been getting some traction. It's certainly worth a look. And then, of course, many of the cloud service providers like AWS or DigitalOcean or Google offer load balancing services as well. Although I will point out most of those are technically just HA proxy as a service, which isn't necessarily a bad thing. OK, and then the second layer, sort of the obvious one, is your application layer. In our demo today, that'll be using Node, but this is effectively just whatever is running your application logic. So it could be anything. And sort of the obvious key there is that you've got multiple of these servers. That's the distributed nature of the application. And then the third layer is the messaging layer. And so this is what I sort of call the magic layer, because it ties it all together, and it takes what appears to the client to be a pool of unrelated servers and makes them appear to be one large server to the user, if it's working correctly. And again, there's a number of different options available for this. So Redis is actually a pretty nice option. You probably know it more as a key value store, but using its pub sub functionality, it can work really, really well as a messaging layer as well. So if you're already using it for caching or something of that nature, it's really nice to be able to plug that messaging layer right in without adding anything else to your stack. There are also dedicated tools such as RabbitMQ or ZeroMQ or a bunch of others that end in MQ if you just search around. And then the final one is Democracy.js. And so this is actually an open source library that we wrote at Goldfire specifically for this use case. And we're going to use it in the demo, and so I'll go over a little bit about the properties of that, how that works. So speaking of, let's go ahead and get into some code. And I know you all are probably going to be disappointed it's not another to-do app, but let's just see how this works. Hopefully the audio is not too loud. OK, so basically it's a really basic application. As you click around on the screen, it draws a dot with a color in the location that you clicked, and then it plays a different pitched tone based on the horizontal location. So it's a fun little application, but it gets sort of boring rather quickly. What would make it a lot more interesting is to add some multiplayer functionality to it. So we're going to do that using WebSockets, and obviously the first step there is to set up our application layer. So let's jump into our code here. And this is the client-side portion. We don't need to worry about this too much. It's mostly boilerplate, actually, pretty short. The basic idea is we've got a click area, which is just a div covering the screen. We add our click listener to that. And then we call this function play audio visual, where we pass the click location, the X and Y. And then in play audio visual, we're just doing some basic DOM operations where we draw the dot, and then we've got an array of different pitch tones that we play based on the X location. So pretty simple. Let's go ahead and set up our Node server, as that's what's going to be our application layer. So let's create server.js. And let's go ahead and default to port 3000. And then, as I mentioned, we'll be using WebSockets. So I'm going to use a library called Primus. And we will go ahead and require that. So what Primus does is it's basically just a wrapper, an API wrapper around other WebSocket libraries that you may be familiar with, like Socket.io or WS, or a variety of other options. OK, so now I'm going to create the Primus server. So that's just primus.create server. And we'll pass in the port. And then we want to define a transformer, which in this case, we're using the WS library. So we just enter WebSockets. And then we want to listen for a connection from the client. And that will pass us, not a message, that'll pass us a WebSocket, so the WebSocket connection coming from the client. And at this point, let's go ahead and just log this so that we can see it happening. OK, we'll log the port. And then the only other thing that we want to do is listen for data coming from the client. So we're going to add the click so that we can send that data from the client. So WebSocket.on, and we will listen on the data event, which will give us a message. And then we just want to broadcast that message to all of the other clients. So we just do that with Primus.write. OK, so that's our entire server. Now we just need to update our client. So I've already got the first part of this written. I'll just uncomment this. So the first thing we're doing is new Primus to open our WebSocket connection. And as we wrote on the server, it's on port 3000. And then we listen for the data. So that's where we broadcast. Each of the clients receives that data. And we'll call that play audio visual function. Then the only other thing is instead of calling that in the click, we want to send that click location to the server. So event.x and event.y. All right, and so that's everything we need to do. Let's go ahead and start our server. And let's open up our application again. So now we've got it on 2 iframes. This would work the same across the internet or different browsers or however you had it set up. But for demonstration purposes, I've just got 2 iframes. And as you can see here, both of them have connected to our server. And now, if we click, it's syncing across. All right? So we've added this multiplayer functionality. Both clients can see everyone else's clicks and hear the sounds that they're playing, so you can interact. But there's still a problem, right? Because if this thing starts to go viral or something and it starts getting a lot more traffic, our little virtual server is not going to be able to handle it. Or even worse, if our server were to go down, lost the mouse. Now, when I click around on the screen, nothing happens. So our application's now completely broken because one server went down. And so we need our distributed system to protect against this. And if you remember, we had the 3 separate layers, right? The load balancer, the application layer, and the messaging layer. We've got our application layer. Let's go ahead and add the load balancing layer. And we are going to be using HAProxy for this. So let's go ahead and set up our haproxy.config file. And it's a really simple config. So we start by defining the front end. And we will bind to whatever port we want. But we'll go ahead and use port 8000. And then we want to define the default backend of sockets. And then we will define that backend and give it a balancing algorithm. So the default balancing algorithm that you'll most commonly run into is round robin, which is usually works pretty well for most use cases. But in our case, where we're using long-lived WebSocket connections, that's going to get very, very out of balance really, really quickly. And so least connections is nice because, as the name implies, the next connection that comes in is going to go to the server that has the least current connections open. All right? So then the only other thing we need to do is define our servers. And we've got one on port 3000. And we'll tell it to check as well, which tells it to do health checks so that it knows when the server is up or down. And then we will define our second server. And that's it. That's our whole configuration. So we will go ahead and start our server, haproxy-f, haproxy.config. And as you'll notice, we've got some warnings here. And that's because I basically left out some boilerplate configuration that you would want on a production setup. For a local demo like this, it's not really necessary. But if you were going to do something production with HA proxy, the documentation is really great, and there's a lot of tutorials out there. So all you got to do is search Google, and you'll find the information. OK, so our config is set up. We need to update just a couple other things. So one aspect on our server, we're still defaulting to port 3000. And so if you notice in our HA proxy, we define 3000 and 3001. So we are just going to do that through command line arguments. So let's just grab that. And then that's all we need to change on our server. That's going to pass that port into our WebSocket configuration. And then on our client, we are also still defaulting to port 3000. So there's a couple issues here. Number one, we're obviously bypassing our load balancer, which is on port 8000, which means we also won't be hitting our 3001 server. But the other issue is the fact that it's really best practice to set up the firewall on your application servers, on the individual ones, to only allow connections to come from the load balancer. So there's almost never a case where on these ports you should be able to connect directly to any individual application server, because those application servers should really be completely interchangeable. So the single point of entry should always be that load balancer. So we will change that to 8000. And let's go ahead and start our two servers. So 3000 and 3001. OK. And we'll reload this. So the first thing you'll notice is in our console here, we've got a connection on 3000 and 3001. So we can see that our load balancer is working. But let's try the application now. So each individual client is working like it was before we added the multiplayer server, but it's not syncing anymore. And the reason for that is because we're missing that magic layer, right, that connects the servers together and makes them function as if they are one. So let's go ahead and add that now as well. And as I mentioned, we'll be using Democracy.js for that. And so we've just already got that installed here through npm. And so we will require democracy. And then we will create a new democracy. I'm sure there's a joke there. And so then all we need to define for a democracy is our source, which is the current server. And so we'll just pass in the port. And then we will define our peers, which are the servers that we defined in our load balancer, which would be port 3000 and port 3001. OK, so our democracy system is set up. Basically, what this is going to start doing is automatically running elections and electing the leader server and then citizens of the democracy. And that will allow you to handle things like state and different more advanced functionality of your distributed system. But for our purposes, we just need to use the pub sub. So first thing we want to do is subscribe to a channel. We won't name it channel. We'll name it global. and then we will listen for data coming across that channel. So we'll listen on global, and that'll give us a message. And then what we want to do is the same thing we did with the WebSockets, is broadcast that message out to all of the connected clients. The other thing we want to do is publish, again on global, and we pass the message. So just real quick to go back over exactly what's happening here. So the client connects to our application. They open a new WebSocket connection through Primus on port 8000, which gets routed through our load balancer and spread out between our two, at this point, application servers. And then on our server, we get that connection event, which gives us that open WebSocket. We then listen for data coming from the client. So when the client clicks, we receive that data. We then broadcast it out over all of the other, including that same open WebSocket connection. And then we publish that data on democracy. So we still want to do both of those because democracy will only publish to the other servers, not to itself. And then all of those other servers will receive on this channel the WebSocket message that we will then broadcast out to all of the clients connected on each of those servers as well. So let's, whoop. OK. So let's go ahead and restart both of our servers and give this a try. OK, so first thing you notice, load balancer is still working. This time, as we click, we're back to having a multiplayer setup, right? From the client's perspective, it appears to be one large server. They have no idea how many servers that are being connected to, and they're all able to interact within the same environment. Now, taking it even further, if, let's say, one of our servers goes down, before, the whole application stopped working. But now, the first thing you notice is that HA proxy immediately detects that that server is down, and it's going to stop sending connections to that server. And then also, you may have noticed that we auto-reconnected the client that was on 3000 over to 3001, or the reverse of that. And if you click, even with one of the servers down, our application is still functioning just fine. Our users have no idea that there are any issues. So now, if you go to this URL, scale.goldfirestudios.com, I've taken the code that we just wrote and uploaded it to 4 DigitalOcean servers. And I have added different colors. You're starting to see a different color to each of the 4 servers, so that when you click on the screen, you'll be able to see the color that corresponds with the server that you are connected to. And we can see it's working now. So this is demonstrating that the load balancer is working because we're being spread evenly across the servers. And it's also showing that the messaging layer is working because you aren't just seeing your own color. As you can see on the screen, you're seeing all 4 colors. So we've got the full distributed system working. And so now we're able to, you probably can't see the URL anymore, but we're now able to handle more traffic. And if 1 or 2 or maybe even 3 of these servers were to go down, the application would still be working. We would just lose some colors in this case. So just to recap, in really just a couple of minutes and a couple lines of code, we've taken a simple client-side application. We've added multiplayer functionality to it, which was our application layer, just using a simple Node server. And then we've added the load balancer to the front, the messaging layer to the back, and we've created a full, simple distributed system. So hopefully, you'll be able to take some of these concepts and start applying them to your own projects after Nordic.js. And I will be uploading the code for this demo as well as the slides here later this afternoon. And so you'll be able to find that on my GitHub at Goldfire. You can also follow me on Twitter, where I will tweet out the link later today at Goldfire Studios. So thank you very much.